Training a massive AI is really a search for perfection. But when you're dealing with billions of parameters, that search can be incredibly painfully slow. So, how do we speed it all up? Well, today we're diving into a really powerful optimization technique that does just that. It's called K-FAC. But, okay, before we get to K-FAC, let's just step back and ask a more basic question. What does it even mean for an AI to learn? I mean, it's way more than just crunching numbers. It's about navigating a space that is almost unimaginably complex. All right, here's the best way to picture it. Imagine you're a hiker, and you've been dropped into this colossal, fog-covered mountain range. Your one and only goal is to find the absolute lowest point, the bottom of the deepest valley. This whole mountain range is what data scientists call the loss landscape, and that deepest point, that represents the absolute best version of the AI model. The lower you go, the smaller the error and the smarter the model gets. So this brings us to the core challenge, what we can call the optimizer's dilemma. I mean, if the entire landscape is hidden in fog, how on earth do you decide which direction to walk? The tool you use to make that critical decision, that's called an optimizer. Well, the most straightforward strategy, right? You just look at the ground right under your feet and take a step in whatever direction is the steepest downhill. This is the whole idea behind gradient descent, and it's really the workhorse of machine learning. It's simple, it's totally intuitive, and hey, it gets you moving in the right direction. But here's the catch. Imagine you're not on an open hill, but in a long, narrow canyon. The steepest path might just send you bouncing from one wall to the other, zigzagging your way down. You're making progress, sure, but it's painfully slow. The steepest immediate step isn't always the most efficient route to where you really want to go. To do better, we need a much smarter approach. We need to move beyond just looking at our own 2 feet and actually try to understand the overall shape, the curvature of the entire valley. And this is exactly where more advanced, what we call second-order optimization methods come into play. And this really gets at the huge difference between the standard gradient and something called the natural gradient. Our simple hiker, they're just following the standard gradient, the steepest path right in front of them. The natural gradient, on the other hand, is like giving that hiker a full-blown topographic map. It takes the entire landscape's curvature into account to find the truly most efficient route, pointing you straight to the bottom of the valley and letting you skip all that annoying zigzagging. So you're probably wondering, where does this magical map come from? Well, it comes from a mathematical tool called the Fisher Information Matrix. Just think of it as the ultimate guide to the lost landscape. It mathematically describes all the curvature, telling the optimizer not just which way is down, but the actual shape of the terrain stretching out in front of you. Having a perfect map sounds amazing, right? Problem solved. But there's a massive problem. For the kinds of giant neural networks we're building today, this map is just impossibly big. And this is where K-FAC comes in with a totally ingenious shortcut. You see, for a big model with billions of parameters, calculating and then inverting the full Fisher matrix would take an absolutely astronomical amount of computing power. It's just not practical. It's like we have the blueprint for the perfect map, but we could never, ever afford to actually print it. K-FAC's solution hinges on a really clever math trick called the Kronecker product. It's basically a way to build a huge, complex matrix, our map, by combining much smaller, simpler ones. So imagine creating a detailed mosaic, not by laying down every single tiny tile one by one, but by arranging just a few simple, repeating patterns of tiles. It's a massive shortcut. Okay, so here's the game plan for how K-FAC actually works. It starts with that perfect but impossibly large Fisher matrix. Then it makes this really clever assumption that this giant matrix can be approximated by combining 2 much smaller ones, using that Kronecker product. This breaks the single, impossible calculation down into a series of much smaller, totally manageable steps. It's a mathematical shortcut that gives us a good enough map without the impossible price tag. Now, having a method that can take these incredibly intelligent, long-range steps, it's like we've swapped out our hiking boots for a Formula One race car. Yeah, it's a whole lot faster, but as you can imagine, it's also a whole lot harder to control. And this quote just nails the point. The original paper puts it perfectly, describing these powerful optimizers as race cars that need way more sophisticated control systems to keep them on the track. If you just floor the accelerator, you're gonna crash. You need brakes, you need steering, and you need a way to adapt to the road ahead. In the world of optimization, that control system is called damping. Damping is just a collection of techniques that act like brakes and a really responsive steering system for our race car. It keeps the optimizer from taking steps that are way too aggressive or just plain wild, making sure our car doesn't go flying off the road when it hits a sharp turn in the lost landscape. And what's so cool is that we can actually see the quality of our map. On the left, that's a sophisticated map made by a K-FAC approximation. The image on the right shows the difference between that map and an even more accurate one. Basically, the darker that right-hand image is, the smaller the difference, which means our map is better. And a better map? Well, that means our race car can navigate the landscape with way, way more precision. Okay, so we've got a faster vehicle and a better map. What does this all actually mean in practice? What's the big payoff here? Well, it's significant. We get AI models that learn faster and much more reliably. Just take a look at these results from a standard AI training benchmark. This chart is showing the training error. The baseline method, over there on the left, it's making progress, but it's kind of slow. Now look at the K-FAC methods next to it. They just dive down to a lower error rate so much faster. The key is they aren't just taking bigger steps, they're taking smarter steps. And we can even put a number on how much better that more detailed map is. The research shows that using that more advanced approximation, the better map we saw a second ago, improves the progress you make in every single step by a whopping 25 to 40% compared to a simpler K-FAC version. I mean, that is a huge leap in efficiency. So let's bring it all together. What have we learned? K-FAC is this super powerful optimizer that goes way beyond simple gradient descent. It understands the curvature of the lost landscape to find the most efficient path down. It gets around the impossible cost of a perfect map by using a clever approximation with the Kronecker product. And it uses damping to keep all that power in check, preventing it from crashing. The end result? AI models that can be trained dramatically faster. And this all leads to a final, really big question. As our AI ambitions keep growing and models get more and more complex, we can't just keep throwing more computing power at the problem forever. So you have to wonder, will elegant, clever mathematics, things just like the approximations inside K-FAC, be the true key that unlocks the next generation of artificial intelligence?